Discover why stronger shear can sometimes produce larger droplets, defying our intuition about emulsion physics. When we apply high shear to an emulsion droplet, we expect it to break into smaller pieces, but sometimes the opposite happens. Let's see this counterintuitive phenomenon through a concrete example. We start with oil droplets, suspended in water in a Quetzal apparatus. With ordinary oil having similar viscosity to water, the droplets break into smaller pieces as we increase shear rate. But when we use thick polymer-laden oil with higher internal viscosity and apply the same shear, the droplets become larger instead of smaller. This paradox reveals a fundamental gap in our understanding of emulsion breakup. The naive textbook formula predicts that droplet size is inversely proportional to shear rate. Stronger shear gives smaller drops. This simple formula misses the crucial role of the viscosity ratio lambda, which is the internal viscosity, divided by external viscosity. Lambda equals mu in divided by mu out. This dimensionless ratio controls how the droplet interior responds to external shear. When lambda is large, the viscous interior suppresses internal circulation, making the droplet more resistant to breakup. We need to correct our scaling law to include the viscosity ratio effect. The corrected formula includes a function f of lambda that multiplies our original scaling. When lambda equals 1, f is approximately 1. As lambda increases, the function f grows, making droplets larger even at the same shear conditions. Let's work through a concrete example to see the paradox in numbers. Suppose f of 1 equals 1, and f of 20 equals approximately 6 for a highly viscous internal phase. If we increase the shear rate by a factor of 3 but switch to a viscous oil with lambda equal to 20, the ratio of new droplet size to old is about 6/3, which equals 2. The droplets are twice as large despite the stronger shear. Let's understand the physics behind why high internal viscosity creates this stiffening effect. In a low lambda droplet like water in water, internal circulation easily develops. The fluid inside recirculates freely. But in a high lambda droplet like honey in water, the interior barely shears. It behaves almost like a solid on the deformation timescale. Internal recirculation is normally beneficial because it spreads stresses and helps necks thin out, facilitating breakup. When lambda is large, the interior has a quasi-solid response. End caps accumulate high normal stresses that delay breakup. We can quantify this with a simple timescale comparison. The internal shear timescale is proportional to droplet radius squared divided by the kinematic viscosity of the internal phase. The deformation timescale imposed by external shear is 1 over shear rate. We define a dimensionless number s as the ratio, shear rate times radius squared divided by internal kinematic viscosity. Consider a 10 micrometer droplet with honey-like viscosity of 1 pascal second at a shear rate of 500 per second. The kinematic viscosity is 1 pascal second divided by 1,000 kilograms per cubic meter, giving 10 to the minus 3 square meters per second. Plugging in numbers, S equals 500 times 10 to the minus 10, divided by 10 to the minus 3, which is 5 times 10 to the minus 5, much less than 1. This tiny S value means the interior hardly has time to shear during the imposed deformation, creating a stiff response. Even in the small deformation regime, classical theory already flags the importance of lambda. G.I. Taylor studied slightly ellipsoidal droplets deforming in gentle linear shear flow. The deformation parameter d, defined as length minus breadth over length plus breadth, equals this fraction times the capillary number. The capillary number is the ratio of viscous stress to interfacial tension. External viscosity times shear rate times radius divided by interfacial tension. The prefactor in Taylor's law depends explicitly on lambda, showing that viscosity ratio affects deformation even before breakup. When lambda equals 1, the prefactor is 35 over 32, about 1.09. When lambda equals 20, the prefactor becomes 396 over 336, about 1.18, which is 8% larger. While this 8% difference seems modest in the linear regime, it gets dramatically amplified in the nonlinear necking and breakup regime. The real mechanism behind the paradox lies in how the breakup threshold shifts with lambda. The critical capillary number for breakup increases with lambda. The threshold shifts upward for more viscous internal phases. Empirically, the critical capillary number follows a power law. CAC of lambda equals CAC 0 times 1 plus alpha lambda to the power beta. Consider CAC 0 equal to 0.4, alpha lambda equal to 4, and beta equal to 1/2. This gives a critical Ca of about 0.4 times root 5, which is approximately 0.89. Now suppose we operate our apparatus at a capillary number of 0.6. Low lambda droplets with threshold below 0.6 break easily into small fragments. High lambda droplets with threshold above 0.6 resist breakup and remain large. At the same operating conditions, we get completely different droplet sizes depending on the internal viscosity, creating the paradox. Let's put all the pieces together to understand this counterintuitive phenomenon. High internal viscosity creates a stiff interior that resists deformation, shifts the breakup threshold higher, and ultimately produces larger droplets despite stronger shear. The apparent paradox disappears when we properly account for how the viscosity ratio modifies both the deformation physics and breakup threshold. Understanding this effect is crucial for rational emulsion design, whether making nanoemulsions, food products, or pharmaceutical formulations.